Hi, my name is Anastasia, and today we will be covering the topic of Introduction to Electrochemical Fundamentals. To start with, we're going to define some core things to understand about electrochemical system, beginning from the electrochemical system itself. Electrochemical system is the system that contains minimum of two electrodes which are separated by electrolyte and connected via an external conductor. Important to understand that ions, they flow through the electrolyte, but electrons, they flow through external conductor. Next definition that we need to understand is what is the electrode itself. Electrode is the part of the system where electrons are mobile species. The electrode could be used to sense or control the potential of these electrons. And also important to understand that most of the time electrodes are metallic or at least a semiconductor. Next definition would be electrolyte. Electrolyte is a part of the system where ions are the mobile species. Also in electrolyte, a free movement of electrons is blocked. Electrolyte could be a molten salt, salt solution, ionic liquids or solids, or polymers. Let's consider following reaction. In this reaction, silver in its plus form reacts with iron in its 2+ form, forming metallic silver and iron in 3+ form. Silver plus in this reaction is an oxidant, where iron 2+ in this reaction is reductant. The reaction of reduction is transformation of silver plus by using one electron to metallic silver, and the reaction of oxidation is a transformation of iron 2+ to iron 3+ with the release of one electron. What is important to remember that oxidation is a loss of electron, while reduction is a gain of electron. And to remember it easily, we could remember a simple acronym: oil rig. Oxidation is a loss, reduction is a gain. Oxidant does an oxidation, but while doing so it gets reduced, while reductant does a reduction, but gets oxidized. In this particular example, silver plus is an oxidized species, while silver metallic is a reduced species. This helps us to form a redox couple. Similarly, iron 2+ and iron 3+ would be a redox couple as well. However, this reaction is not full unless we include ions of the reaction as well. So net reaction would be silver nitrate with iron nitrate forming silver metallic, as well as iron 3+ nitrate. Moving further, let's remember some of the thermodynamics basics from our general chemistry course. One of the most important formulas in thermodynamics from the general chemistry is Gibbs free energy in equilibrium. Delta G of reaction equals delta G naught plus RT ln Q, where delta G naught is the free energy at a standard state. Logarithm of K represents here an equilibrium constant. So let's consider the reaction where A plus B equals C plus D. This reaction has a certain Gibbs energy, some certain free energy. So in this particular example, our equilibrium constant will be a proportion between concentration of reagents to the concentrations of the product of reaction. And at the equilibrium point, delta G actually equals 0. However, at non-equilibrium point, concentrations would differ, resulting in a different value than delta G equals 0. So now, remembering that, let's move to thermodynamics in electrochemistry. One of the most important points to consider, that's our potential E, which equals to the ability of system to produce work, ability of the system to work. Let's consider a following reaction, which will be seen a lot more times in electrochemistry, where hydrogen is being transformed into two hydrogen pluses into protons. And also we have silver plus that will be transformed into metallic silver. And then below the line, you can see the summary of this reaction. Let's consider free energy of this reaction. Free energy of this reaction at a standard state would equals the sum of the free energy of products minus sum of free energy of reactants. And if to calculate the standard values, we could get a value of minus 154 kilojoule per mole, where minus before the value indicates the spontaneity of the reaction. So this reaction happens spontaneously without any work applied to it. Moving towards electrochemistry, we should consider the reaction of delta G equals minus N, F, and E cell, potential of the cell, where F corresponds to Faraday constant 96,485 coulombs per mole, and N corresponds to the number of electrons being transferred in the reaction. If to plug in the value of the spontaneous reaction that we calculated with the free energy on our left, we could see that potential of the cell equals positive 0.79 volts. And this also indicates a spontaneous reaction. So it's an opposite value where plus in the potential means the spontaneity of the reaction. Moving further, let's consider a simple electrochemical system. In this system, anode does oxidation and cathode does reduction. Let's imagine a simple scheme of electrochemical process. In this system, our cathode has certain energy, and how you should understand this portion is that this energy is quite high. So to do the electron transfer into our solution in our electrolyte from the electrode, energy of the solution should be significantly lower than the energy of the cathode, so then this electron would be able to transfer. And also what we need to consider, it's not only movement of the electrons, but also its movement of ions in the solution, where positive ions are being drawn to the cathode and negative ions being drawn to the electrode, and then overall this creates some sort of ion movement in our electrolyte. So now we have our electron in the solution. So if we would like to draw our electron outside of the solution, the energy of our anode should be significantly lower than the energy of the solution. Then this reaction would occur naturally, where electron will be in a way automatically drawn to a lower energy barrier, and then it will move from solution to our anode. And this reaction could be driven by potential applied in between those cathodes and anodes, so outside potential. Moving further, let's discuss potentials in this system. What is important to understand that in electrochemistry, all of the reactions that are happening in separate places. Our oxidation takes place in one spot and our reduction takes place in another spot. This is the reason why us electrochemists write the reactions in half reactions way, representing separately potential of the cathode and separately potential of the anode. So potentials of those half reactions. So looking back at the reaction presented earlier, we could see that potential of this particular hydrogen transformation equals 0. And this is a separate concept to understand because this is generally assumed by electrochemists, where this reaction would be at particularly 0 volts, and this is used further in referencing systems and so on. So this is something that you would meet quite frequently in electrochemical systems. And then our second reaction of silver plus going to metallic silver has a potential of 0.79 volts. So now, summarizing this reaction to figure out the potential of the cell itself, we could summarize potential of the cathode as well as the potential of anode. And then from the reaction that we know before, which describes Gibbs free energy, we could think about our Q value as a concentration of our reduced species to the concentration of our oxidized species, hence transforming it into Nernst equation. Nernst equation is one of the most important equations in electrochemistry, which completely describes thermodynamics, mostly in the standard state of this reaction, and this is a crucial equation to remember. Now let's move to the concepts of kinetics in electrochemistry. One of the most important things to know in electrochemical kinetics is that current across electrode and solution interface depends on the potential. Let's look at the reaction that we already discussed before. If to imagine this reaction happening in the actual electrochemical system, we could imagine it this way. In this electrochemical system, we have our hydrogen gas being bubbled into acidic solution, And this system also has 3 electrodes. So it's a 3-electrode system, which has working electrode, reference electrode, and counter electrode. Our reference electrode is here to help us to detect the potential in the cell where current is flowing between working and counter electrode, where our working electrode being some reactive metal. Imagine in this system, let's look at the current response that we can get while applying potential to it. In this system, we have our current axis, where plus is referring to oxidation of species and minus is referring to reduction of species, and our x-axis has a value of an overpotential. Overpotential, that's that extra bit of work that you have to apply to make sure that you're driving the reaction. So that's the potential that we're applying on top of pre-existing Nernst equation conditions, right? So it's a bit of that work that we need to drive the reaction further. In this system, our current response will be recorded at such a black curve represented on the graph. As an example, we will be considering our working electrode as a platinum. Platinum, being a very active metal, requires a very small amount of extra work applied to the system to drive the reaction. Starting from the point 0, where point 0 is pretty much the potential that we need according to Nernst equation, we need a very small amount of overpotential for the platinum to drive the reaction. And this reaction would be making of hydrogen, hence reduction reaction. On the other side of this graph, we could see our hydrogen oxidation, and you see that it stabilizes over the time, but it doesn't really go according to our Nernstian prediction. The small difference over here corresponds to the mass transfer limiting current. So this mass transfer limiting current indicates one very simple thing. Our hydrogen gas needs some time to arrive to the electrode surface where the reaction would occur. Let's consider another situation where we would use a little less active metal in our 3-electrode system. In this system, we would replace our working electrode with another metal, let's say nickel. Then our current response versus overpotential applied would look completely different from what it looked for the platinum. And one of the most important points to understand is the fact that now we have to apply much higher overpotential to be able to drive exactly the same reaction of making hydrogen in comparison to our platinum. Additionally, another thing to consider is that now to drive the oxidation reaction of our hydrogen, we also need much more overpotential going other direction. This indicates that metal such nickel would be less active in comparison to platinum. And then going further, we can actually consider even next metal, which would be gold, which would be even less active than the nickel that we just discussed. This region over here, where we can judge on how much overpotential we need to drive the reaction of hydrogen evolution to produce our hydrogen, is called Tafel region. Tafel region is described by the following equation, where E naught is an exchange current as a prefactor. This is something that describes how fast our reaction is happening and corresponds to the kinetics of the reaction. Moving forward, let's discuss transport in the electrochemical systems. Let's consider very well-known Ohm's law. Ohm's law is actually a law that pretty much describes the transport in the system. In this image, our potential, this is something that pushing our currents through the system, potential being expressed in volts and current being expressed in amps. So we can understand transport this way. This is something that is moving through the system. The idea of Ohm's law is mostly applicable for the electrons, but if to translate this knowledge into electrochemical system, this simple migration or diffusion would be working only in those systems where concentration is extremely high and this concentration of species does not change over the time. However, in a more realistic systems, transport is much more complex phenomenon, and I would like to discuss it next. In the real system, such thing as concentration gradient or diffusion exists. And you know this very well from such a simple reaction where we would drop something with a higher concentration, let's say a dye, in a jar of water, and we could see how slowly it diffused through the system, and then the system overall is taking this middle ground between a very concentrated dye that we dropped versus water which we dropped it in. This phenomena is described by Fick's first law, and this law is described by the following equation. In this equation, we have our flux, which is described in moles per centimeter square per second. So it's how much of that substance can be distributed over the area within certain time. We have our diffusion coefficient, and we have our gradient in concentration. Gradient in concentration could be understood by a simple change of the concentration over the time. Now I would like to introduce the very last and probably one of the most important concepts in electrochemistry, which is still being heavily debated and still being studied, such as the electrical double layer. When we think about electrochemical system, we know we have our supporting electrolyte, which has some molecules of the solvent floating around, as well as anions and cations in the system. Let's imagine our electrochemical system with the electrode which has a positive bias, so we have a positive charge on the electrode. Our supporting electrolyte anions would be naturally drawn to this electrode, but they will not be neutralized. They will be drawn to it, and they will arrange on the surface of this electrode in this very orderly fashion, and this is something that is called inner Helmholtz plane. Moving further, we have our diffuse layer. Diffuse layer is distributed within a free volume of our electrochemical system, and it mostly composed of our cations surrounded by solvent molecules, creating this hydration shell around it. So what happens, because we have our anions neatly lined up on the surface of the electrode, some of the cations with the shell outside of it will be naturally drawn to our anions, forming this very orderly layer. This layer is called outer Helmholtz plane. And these two planes, inner and outer Helmholtz plane, they're forming the electrical double layer. What is important to understand about the electrical double layer is that the orientation of these ions is completely different from the bulk of our electrolyte solution. Another important thing to understand is this electrical double layer acts as a capacitor, hence it's storing charge in between these planes. And also that this charge is not being neutralized, even though that we have our positive electrode and our negative anions drawn to it, this charge is not being neutralized. It is a very difficult concept in electrochemistry, which is still being researched. So this is a very superficial explanation of the electrical double layer, and it definitely requires more reading. Thank you very much for your attention.